Hi everyone. I hope the audio and video quality is good. So let's wait for a few more seconds and we can get started. I think it looks good. We can get started. So in today's session, oh, it's a bit quiet. Let me increase my volume. I think this is good now. Okay, cool. So in today's session, we'll be learning about linear regression, and I'm starting a new series, deep learning series. And in the upcoming sessions, if I'm doing some machine learning, you'll be seeing I'm covering these sessions like linear regression, logistic regression, convolutional neural network, recurrent neural network, and transformers. So I will explain all these things. And also you can see some other sessions from team. We both will be doing some sessions in this year. So you can see the upcoming sessions here. Cool. So over the past few weeks, I mainly covered FastAI library, and we have covered 8 lessons from the FastAI. I think that's pretty much really good lessons. I think now we are going to dive deep into PyTorch library. We'll be implementing lots of deep learning algorithms using PyTorch, and we'll be using FastAI and transformers libraries. So before going here, let me explain what is deep learning, and then we can get started with linear regression. And in the upcoming sessions, we will go through one by one each topic. So that's the goal of today's session. So also I have some plans to cover, like what is deep learning, what's the current status of deep learning, and what is supervised learning, and we'll be preparing some small data set, and then we'll be implementing linear model, and we will understand how gradient descent algorithm work, and we'll be implementing everything using PyTorch. So that's the agenda and goal of today's session. So let's see what is deep learning first. So this is from deep learning book from Ian Goodfellow and a few others. So I'm going to use this as an overview of what is deep learning. If you see, there are like 4 main things: artificial intelligence, machine learning, and representation learning. We usually call both as like a deep learning. So it's like you can assume this is like deep learning, and there is machine learning, and there is artificial intelligence. So what's exactly the difference between each 3 different areas? So if you see anything that has some intelligence, we can call that as artificial intelligence. And in machine learning, we use some data set, like learning something from the data, and it's not usually deep, it's shallow. I will explain what does it mean. And we need to create some features here, and our machine algorithms uses those features, and it does some mapping. So that's machine learning. But in deep learning, we have some hierarchical representation. We no need to create any features. We'll be creating lots and lots of layers. I will explain all these things, but in high level, we no need to create lots of features. It's like a representation. You create a huge structure, and the models will learn something in that structure. So that's the main difference between artificial intelligence, machine learning, and deep learning. Also, I'll show you one more thing. So there are some things like rule-based, classic machine learning, and representation learning, which is deep learning. So the main difference in each is, so if you see rule-based, we have some input, and we write lots and lots of code, and then we will get some output. So that's basic rule-based algorithms. And there are classic machine learning. So here what it does is we have some input, and we design some features. That features helps the model to learn something in the data. and then mapping from features, then we will get some output. But in deep learning, what we do is we have some input. We rarely create any features, but we will create lots and lots of additional layers of abstract features. Then the mapping will happen automatically and you will get the output. So I'll show you a few other things. So let's see what deep learning currently does. So if you see, there are so many applications in every field, but I'm going to talk about just two. One is introducing Whisper. So this is like a cutting edge deep learning model that automatically identifies voice to text. So if you upload any video, it uses deep learning and then it converts that as a text. So it's a great example of deep learning. So generally speaking, let's say you have some audio. There is no way to write code to understand the audio. But what we can do is we can create some representation learning. So it's like we have some input and you create a huge structure like this. Then the model will learn to map something and then you will get the output. So if you see this chart, so that's what's going here. So you have some input, then you will create some lots and lots of features, which is like a layer and lots of algorithms, and you will get the output. There is no way to complete this task using rule based, this one. So it's impossible to do that. So deep learning shines in these areas where you cannot map input and output using rules, but you can create some algorithm and the algorithm will try to learn something from the data mapping. You try to map the input and the output using all the different layers and it will learn something clever things here. So in our future sessions, we will try to understand how to design these things. But in high level, this is one of the example of deep learning. I'll show you one more thing. I think this is also another great example of deep learning. So what happens here is you just create some text and then from the text it creates this image. So all these images created by computer. So that's one of the fascinating thing from deep learning. So we cannot create any rules to do that. So we will create lots different representation and then during training it maps the input and output. So we will get outputs like this. So this is a great example of deep learning. Cool. I think with these two examples, these are very relevant and new. This is like a cutting edge thing in deep learning. And over the past few months, we learned about FastAI library and Jeremy Howard, who's the creator of FastAI and the course, who's just started teaching a new course on stable diffusion models. So I think it will be released end of this year or early next year. So we can continue working on those in the next year, early next year. So that's one of the goal for early next year. Cool. I think I covered first two. Now let's talk about what is supervised learning. So let me use my notebook. Cool. So in supervised, there are few things. So in machine learning or deep learning, we can broadly classify into few things, mainly maybe two: supervised and unsupervised. So in supervised learning, the main thing is you know the input and output. For example, input should be some image and output says this is cat. In another sentence, like in another example, input should be like a text and output should be this is like a positive sentence or a negative sentiments. And from the two examples I showed recently, the input is audio and output is text. Then in another one, stable diffusion, the input is some text, output is image, generated image. So this is supervised learning. In supervised learning, we know the input and we know the output. In unsupervised learning, we just have the data and we don't know the output. We just use the data to learn some mapping, like learn some groupings and representation. This is unsupervised. I think mainly in our deep learning sessions, we focus more on supervised learning. So if you see the algorithms, linear regression, logistic regression, convolutional neural network, recurrent neural network, and transformers, they all use supervised learning, meaning we know the input and output and we are trying to learn something from the data. Maybe I can give you some small examples in each topic. Let's say, maybe let me write here. So in linear regression means you try to predict real number. For example, let's say you have some data and you are trying to predict house price. This is an example of linear regression. And in another case, let's say you have some data and you are trying to predict how much loan you can get. And another thing is, let's say you have some conditions in some games and you are trying to predict the output score. So these are real numbers, because let's say the output score is like 1 to 500, you'll predict some real number. In how much you loan, it's like, let's say 10k to 1 million. This is like a real number. And house price, let's say this is 50k to 1 million, something like that, some real number. So that is linear regression. In logistic regression, we try to predict some labels like 0 or 1. For example, whether this house is greater than 500k, yes or no. For example, whether should bank give you loan or not. This is logistic regression, 0 or 1. There is some small extension of logistic regression. We can call that as multi-class. This is like more than one class. So generally, these are like binary classification. So in binary classification, the output label is like 0 or 1, just 2. But in multi-class, we will be having more than 2 output. For example, let's say you have some chest X-ray images and the output is like whether that's like COVID, non-COVID, pneumonia. So this is like multi-class. Then convolutional neural network and recurrent neural networks. Let's say you have some image and you are trying to predict the output of the image. For example, let's say this is cat image and the output is like cat. So for these learnings, you can use normal deep learning. Also, you can use a special type of deep learning model called convolutional neural network. So we will be learning that after completing logistic regression, we will learn convolutional neural networks. And let's say you have got some text, like I like this movie. So let's say you have some sentence, big sentence like this, lots of sentence, and the output is whether you like the movie or not. Sentiment, positive or negative. So this is like text. So we are trying to learn some pattern from the text. So we can call this as a recurrent neural network. So in recurrent neural networks, we try to learn some history. Like, for example, this movie depends on the input of this, like, I. So it's like that. So there is some recurrent pattern. So after completing convolutional neural network, we'll be learning recurrent neural networks. And there are some small variants in recurrent neural networks like LSTM, gated recurrent neural networks, like that. So we'll be learning those things too. And after completing recurrent neural network, we'll be learning transformers models. So if you see the image I showed previously, these are like transformer models. It's like they have encoder and decoder, and we'll be learning this in our upcoming sessions too. So it's called transformer, encoder and decoder. Cool. I think with this intro, let's dive into linear regression models. So far we have completed what is deep learning and what deep learning does now, and what is supervised learning. And now we are going to work on preparing a small data set, and then we can implement linear models and gradient descent algorithms using PyTorch. So I'm going to create a small data set. Before that, maybe let's create a data set first, and then we can do some coding. So data set. So the data set I'm going to develop is, I'm going to create an algorithm that maps kilometer to miles. So let's say if someone asks you, like, what is 126 kilometer, convert this to miles. So sometimes we cannot calculate this quickly, so unless you know the mapping. So what we can do is, we will try to collect very few data, like 4 data. Let's say you have got some friend, he knows how to convert 1 kilometer. Sorry, maybe 1. Let's say he knows only 4 things. What is 1 kilometer, and convert this to miles, 2, convert this to miles, like that. Only 4 data. With 4 data, we will learn some pattern, and then after that, we can map anything. So this is like a very small, simple example, but whatever we are going to learn, that extends to any number of columns. So let's say you have got here, this is only one input and one output, but the same concept applies to 10 input and 1 output. For example, house price. In house price, you have a number of bedrooms, bathrooms, square feet, location, and then you try to match the output, which is price. So whatever we are going to learn in this simple data set, the same concept applies to any number of columns and any complex data sets. So let's get started. So let's say 1 mile. So 1 kilometer is 0.621. 62. Okay, 0.621, and 2 is 1.242, and 3 is 1.864, and 4 is 2.485. So we have collected 4 samples, and we are going to implement a linear regression model, and then the model will finally say what is the output for 126 kilometer. Maybe let me see the output first and see whether our model learns this. So 126 is 78.29. If our model says 78.29, then that's a good model. It learns something from the data. So let's implement this. Cool. And I'll be doing some basic Python coding. And then while writing something specific to deep learning, I will explain everything there. Okay. So I'm going to use PyTorch library. So if this is your first session seeing this Google Colab, so this is like Google Colab. Here you can create some heading, and then you can click connect. And let's say you are doing some deep learning with image and or any big neural network, you can use GPU to use that. Click change runtime type. Here you can choose GPUs. So for now it's not needed because ours is like a toy example. So just click connect, and let me start typing something. Import torch, and let's check the version. Torch dot underscore version. It's create connected. Okay, so I'm using torch 1.12. So I'm going to use some basic libraries: NumPy, numerical Python, then some visualization. So now let's create some dataset. So we already created kilometer and miles. So our input is X and output is Y. So X data is 1, 2, 3, 4, and Y data is 0.621, 1.242, and 1.864, and 2.485. Okay, maybe let's plot this. plt.plot x data, y data. So you'll see a straight line. So this is like a linear model. So our model is going to learn this pattern. So it's going to learn the slope, and if there is any intercept, it's also going to learn that. Cool. So now what we are going to do is how to map the input to output. So let's create some forward. So in PyTorch, when you do some prediction, we can call that as a forward, because forward means, maybe let me write this. Let's say you have some input and you put the input to models. In model has so many different layers. So each layer, it's doing some calculations, and then it passing the output to the next layer, and finally you get some output. So this is, we can call this as forward pass. And as I said before, each layer has some weights and biases. So these weights and biases are like a random number in the beginning, and during training those weights and biases will update itself to reduce the loss. So let's say you have some input and you pass all the layer and you get the output. Then let's assume this output is 3, but the real output is 6. So this is prediction and this is truth. So we can calculate the error. The error is like 3 minus 6 whole square. Let's say you are using mean square error, then this is you need to square, so this is your error. Then what you do is you try to update these weights and bias to reduce this error. For example, 3 square, that is 9. You try to change all your weights and bias so that this number should go down in next iteration. So this is what happening in the training. So the general high level idea is like this: you have some input and you have some output, then you pass the input to the model, then the model will predict something, y prediction. Then using real truth and y prediction, you calculate the loss. So there are a few ways to calculate the loss, but for simplicity, let's assume we can use mean square error. Cool. Once the loss is calculated, you can update the model because the model has weights and biases. update. So while updating, we can call this as backpropagation. So backpropagation means finding weights and gradient of weights and biases, like how much we need to change, on what direction to change. So those kind of things we'll be finding there, and then we update those weights and biases, and this concept is called gradient descent. So I'll be explaining gradient descent and backprop in detail, but in high level overview, let's assume you find some prediction and you calculate the loss. Then during backpropagation, you find the gradient of all the weights and biases. Then you use those gradient to update those weights and biases. That process is called gradient descent. Cool. I think this should be fine for the high level overview. Now let's start implementing something. So def forward. So to make some prediction, we need to know what is x, and then the output is x is multiplied with some weights. So this is like a simple problem. We no need to have bias. We can just use weights, and maybe we can initialize weights as 2.3, some random number. We usually initialize as a random number. Then during training, this number will be more meaningful to solve this problem. Cool. Okay. Now let's ask our question. What is the miles for 126 kilometer? So let's simply ask something. Forward of 126. Currently it says 289, but we know the real output is 78.29. So this is like a huge loss, and during training we can make that work perfect. So let me check. Cool. Okay. Now let's calculate the loss, def loss. So maybe for simplicity, I'm going to explain different ways to calculate loss. Let's say you have some input, and let's say you have some output, and the model prediction is something. Let's say it's 2, and this is output is 4. 3, output is 6. Maybe let's change this. 3, let's say the output is 8. For 4, let's say the output is 2, something like that. So if you see this example, let's try to calculate the loss. Maybe for simplicity, let's assume loss is y prediction minus y. If you do that, y prediction is 4, 4 minus 2, 2, then 8 minus 3, 5, 2 minus 4, 2, minus 2. So if you see this, then let's say you want to calculate the average loss. To calculate average, you sum everything and divide it by overall. So in this case, 2 and minus 2 will cancel each out, and then you will get only 5. 5 divided by 3, this is your loss, mean square error. Sorry, let's say this is average loss. Okay, but here is a mistake, right? Because 2 and minus 2, it cancel each other, so that's a mistake. How to avoid this is, maybe you can add, yeah, a second, absolute, take absolute of y prediction minus y. So this is one way. So in this case, what it does is 4 minus 2 becomes 2, 8 minus 3 becomes 5, 2 minus 2 becomes minus 2. Then if you take absolute, that becomes 2. Now you can calculate the loss. 5 plus 2 plus 2, that's 9. 9 divided by 3, this is our mean absolute error. We call this as MAE. So there is one more way to avoid this positive plus 2 and minus 2 issue. Just take a square. So if you take a square, this minus 2 and plus 2, that becomes more meaningful. It won't cancel each other. So let's do that. y prediction minus y the whole square. If you do that, 4 minus 2 the whole square, so that's 4, 8 minus the square 25, then 2 minus 4 is minus 2 square is 4. In this case you will get 29 33 by 3. This is your mean square error. Since we are taking the square, let's say generally while reporting we report as root mean square error, because we try to negate the square we have done, which is just a square root of MSC. So optimizing mean square error is as same as optimizing root mean square error. So we no need to worry about root mean square error now. Just use this and then optimize that. So now I'm going to implement this mean square error in code. Let's do that. So loss. So to calculate the loss, let's say you have got input and output, and then you make a prediction, y prediction equal to forward of x. Then using the prediction, you try to calculate the loss. The loss is y pred minus y whole square. So this is your loss. Cool. Now let's try to see how these numbers work. We know that when w equal to 0.621, the ideal, but if you see this, the ideal weight should be 0.621. If you see the code, it says for an approximate result, divide the length by 1.609. So which is same as multiplying that with that number. Cool. So we know that this is like a ideal weight 0.621, but for, let's assume we don't know that number, we will try to figure it out. So how we are going to figure it out is, let's say I want to experiment what happens to our loss for number ranges from 0 to, let's say, 2. 0 to 2 in the interval 0.1, calculate the loss and see for which number we are getting loss is 0. When loss is 0, that number is really good. So let's do that, which is the minimum loss. Let's find that. So I'm going to create a list, weight list, then mean square error list. Then for w in range 0 to 2.1 in the interval of 0.1, let's print weight. Okay. Then for each data, we are going to calculate the loss, and then we are going to sum the loss to find the average mean square error. So let's do that. So let's assume loss sum is 0 initially, and then for each data point, x val comma y val in zip of both the list, which is x data comma y data, then I'm calculating the loss. So what I'm doing here is I'm taking each sample and then I'm putting that sample to the loss. This loss will give me some number, and that number is stored in L, and then we are going to add that number to the loss sum. Okay, I think we found the sum. Now let's print the average. Mean square error equal to L sum divided by length of x data. So let's say you have 4 sample, you need to divide by 4. Okay. Now once we are printing, let's print some way to identify the next ones. Then I am putting all my weights and mean square error to weight list and weight to the wait list and mean square error to the MSE list, so that we can visualize and find the perfect W. So W list dot append W, and then MSE list dot append. Let's copy this one. Okay, now let's run this. Oh, I forgot the comma. Okay. So when W equal to 0, the loss is 2.89, and then when W increases, the loss decreases. You can see when W equal to 0.1 means the loss is 2.03. Then when W is 0.2 means is 1.3. Now the loss is 0.77, 0.36, 0.11, and it's close to 0 when it's 0.6. That's a good observation here. So when W equal to 0.6, the loss is 0. Let's stop here and check some questions. Yeah, sure. I'll share the notebook. Thanks, Tim. Okay. When W equal to 0.6, the loss is 0. This is like a good observation. Now what we are going to do is we are making a model that optimize the W, and it finds this number automatically. We no need to go through one by one and see which is the best one. The model will do that for you. So after this one, if W increases, the loss increases. Good. When W equal to 2, the loss is really high. Now what we are going to do is we are going to plot this and see how that looks. plt.plot W list, plt.plot W list, comma, mean square error list. So it looks like this. When W equal to 0.6, I think the loss is close to 0. So this is like a good observation here. After this one, if W increases, the loss also increases. Here, if W increases, the loss decreases. After this point, if W increases, the loss increases. This is very good observation. Let me explain this with gradient descent algorithm. I'm going to plot similar things. So let's say this is our W and this is our loss. And let's assume the shape looks like this. Okay. So let's assume this looks like this. 0, 1. Let's assume this is 2, 3, 4, like this. Also, let's assume initially our weight is, maybe I'm going to create two scenarios. In scenario 1, let's assume our weight is here. Okay, this is our initial weight, which is somewhere between 0.9 or 0.8. Now let's see what happens. So I am currently here. So this is my initial W. What I'm going to do is I'm going to increase my W a little bit and see what happens to the loss. If I increase my W to 1.2, 1.2, the loss decreases, right? Because let's say this is 1.2 and the loss is decreased. Initially it's here and after that it decreases. Then if I keep on increasing this, it decreases. Then after here, after crossing the 2, if I increase my W, the loss increases. So this is a good observation. In this point, the gradient is like negative gradient. Which means if I change x-axis, if I increase the x-axis, the y-axis decreases, which is negative gradient. Then in gradient descent update, what we do is, if it's negative gradient, we change the direction. So it becomes positive, then you go to the positive direction. This is one example. Now I'm going to show you one more example. Let's say your initial gradient is here. Okay, initial weight is here. Let's assume this is like 3, w equal to 3. We know that when w equal to 2, that's a best one. We need to find a way to go to w equal to 2. What we do is, let's here. What I'm going to do is, I'm going to increase my w a little bit. If I increase my w a little bit, the loss increases. It goes here. If I change my w here to here, the loss increases. You can see it here. So what I need to do is, I need to change my direction. I need to go to the opposite direction. So I will go here, I will go here, I will go here. Slowly I will go here, and then I will reach this point, and the loss is like gradient is close to 0 at that level, so it stops. So let's assume you are here, and then you are slowly going to this direction. How fast we want to go to that direction, that is called learning rate. If you want to go very slow, your learning rate should be like this. It goes very, very slow. If you want to go fast, you increase the learning rate and you'll be here. Then in next iteration you'll be here. Sorry. Then next iteration you'll be here, like that. So in our previous sessions, we learned to use FastAI library. So that FastAI library automatically finds a perfect learning rate for complex problems or data sets. For this session, for simplicity, we can assume the learning rate is 0.01, something like that. So now let's revisit gradient descent algorithm. In gradient descent, what we are going to do is, let's say you are going to update the weights, w minus alpha and derivative of loss with respect to weight. So this alpha is like learning rate, and this part, derivative of loss with respect to weight, this is just a gradient. We can call this as gradient or slope, a few other names. So this process is called gradient descent algorithm. So we are going to implement that now. Before that, how do I find the gradient? I explained the gradient by moving this a little bit and see what happens. But now let's formally calculate the gradient. So how we are going to do that is, so let's say y prediction is xw and the loss is y prediction minus y whole square. Let's say this is the loss, and let's put let's replace y prediction with xw. Then in this case it becomes xw minus y the whole square. Now this is like a minus b whole square, which is a square minus 2ab plus b square. So this is the formula. Now let's expand this with that formula. Then it becomes x square w square minus 2xwy plus y square. So this is our loss. Now we need to calculate the gradient with respect to weight. So it becomes loss with respect to weight. Then if you take a derivative of this equation with weight, this x square w square becomes 2x square w. Then this becomes minus 2xy. Then there is no w term here, then this becomes 0. Then if you take the common thing, which is 2x, then it becomes xw minus y. So this is your gradient for that problem. So So this is our gradient. This problem is very simple one. We calculate the gradient by hand ourselves. But let's say you have a deep neural network. It's impossible to calculate the gradient for each weights with respect to loss. In that case, we use libraries like PyTorch, TensorFlow that calculates the gradient for you. You don't need to find any formula. It calculates the gradient for you. So that's why we are using those libraries in deep learning. So now let's put this in Python code, and then we will try to optimize this. So now I'm going to talk about implementing gradient descent. So I'm going to copy paste my data set, X data and Y data. And let's also copy paste the formula, forward and loss, so that we can see everything in the same screen. And loss. Okay. So now I'm going to also let's assume some w equal to, let's say w equal to 2.2. So this initial w is like a random number. Let me write that. During training, this number will be meaningful. Cool. So we have written how to calculate the output and how to calculate the loss. Now I'm going to write how to calculate the derivative, which is gradient, which is also called slope. So now I'm going to put this equation as a code. So def gradient. To calculate gradient, I need x and y. Then return 2 multiplied by x multiplied by x w minus y. So this is my gradient. So we also asked a question. What happens for 126 kilometer? So let's ask this. Maybe let me put this prediction for 126 kilometer. It says 277. Maybe let me write miles. Okay, so our initial model says 126 kilometers is 277 miles. We know that this is wrong. Now let's do some training and see what happens. So in deep learning, what we usually do is we don't train a model once. We will be passing the data many times. We call it as epoch. So one epoch means passing all the data to the models at once. One epoch means passing all the data. I think this is good. Passing all the data to the models. It could be batch or all the data, but for simplicity, let's say we are passing data one by one. Let's say we have got 4 data points. If I pass all the data points to the model one by one, we can call that as a one epoch. Next epoch 2. Epoch 2 means I'm going to pass the same data one more time. So that's epoch 2. So in deep learning, we train a model for few epochs, like 10 epoch, 20 epochs. It depends on the data set and complex of the problem and learning rate and many other factors. So now for simplicity, I'm going to train for 10 epoch and see what happens. For epoch in range 10, for x comma y in zip x data comma y data, then calculate the loss, Then do gradient descent update. Gradient descent update is W equal to W minus learning rate, which is 0.01. We can use any number. I'm using 0.01, any small number like 0.001 or 0.01, like that. Then I'm going to find the gradient x comma y. Okay. Now after one epoch, let's print what happens to the loss and what happens to the weight. Print after after epoch maybe let me start with 1 to 11. Okay, after epoch 1 the loss is, what I need to do is this is individual loss. Maybe let me create one more sum, loss sum equal to 0, and then put this loss to the loss sum. L sum plus equal to L. Okay, then finally you can calculate the loss, L sum divided by length of x data. So that gives you average loss, mean square error, which is mean square error. Okay. After epoch, some epoch, the loss is this one, and also let's print weight. W equal to W. Okay, I think this is good. Now let's run this and see what happens. Okay, so initially after epoch 1 the loss is 13 and W is 1.4. then after few epoch the loss is close to 0. You can see it here. After 9th epoch the loss is 0.0002, and after 10 epoch the loss is even lesser. So sometimes beginners, they might think this is like 5.5, but you need to see this on this one. This is scientific notation. This is 0.0005. So you need to see this number. This is good. So this is even lesser than previous one. And then we know that the W is 0.62, which is correct, close, 0.621, and we are getting 0.622, which is pretty good. Now we can ask what happens prediction for 126 kilometer. Let's use the model and see what happens. So it says 78.48 miles, which is 78.29. Ours is 78.48, which is pretty close. So with just 4 data points, we learned a model to predict this accurately for any data. The idea is not just finding this number. This is whatever you're doing here, we can apply that for any complex patterns. So that's the main important takeaway. Actually, I thought of covering, instead of writing the gradient by ourselves, I thought of creating a PyTorch code that calculates the gradient for yourself. Maybe we can do that in my next session. I think this is a good way to end today's session. See you all next time. If you have any questions, please ask on Slack. Thank you. Bye.